Solid Edge is the absolute best tool for design repurposing using synchronous technology. Synchronous technology enables us to easily take an existing design and reimagine and repurpose it by precisely morphing and changing it for better aesthetics, for improved performance, or for a completely different purpose. This is a great time saver over starting from a blank slate. In this example, let's use synchronous technology to completely redesign this jack stand from the square-based design on the left to the pyramid-based tubular design on the right. Notice that we are in an assembly, and yet we can select faces of parts and modify them directly without actually diving into the part model itself. Notice how the offset design intent relationship automatically keeps the inside face of the recessed area parallel to the face we're rotating. This saves us time by not requiring us to go in and out of the part in assembly environments to make the changes. The beauty of the design intent relationship is that we can change our minds about what is important and change the design intent at will, with no regard to how the model was created. By disabling the offset design intent, we can remove the bottom plate by simply dragging the bottom face up to the point where it disappears. We can use this same technique to remove the recessed area of the angled ribs. The Selection Manager tool enables us to interrogate the model automatically to detect and find all the rounded corners that contain the same radius, and in this case we'll use the selection to remove these rounds. Synchronous technology maintains symmetry in the model by recognizing another design intent relationship as we drag the face to the corner of the rectangular section. Note that all the sides are also updated to reflect the same change due to design intent and patterning. Just like the first edit we made, we'll select the side face and rotate it by strategically relocating the steering wheel to the top vertex to rotate the faces to converge to form the pyramid shape. Keep in mind we're still modifying this base without ever leaving the assembly environment. Just one more synchronous drag required to open up the base. Features can be temporarily removed to allow drastic changes to geometry and then reattached later. Changes can also be made by selecting geometry, like rounds, and changing their values directly. You can even add equations and let Solid Edge do the math to get the right dimension. By adding full rounds to the corners, we can easily change this design from square to round. Now that this drastic design change in this area is complete, we can reattach the whole. Now let's see how we can modify the part by adding PMI dimensions directly to the 3D model. Locking dimensions allows us to create a permanent distance between the end of the center post and the locking pin hole. Finally, let's change the overall height of the base by adding one more PMI dimension. Notice how the lock dimension maintains the hole relative to the end of the post. Now that we have the shape we want, let's add a few more features to complete the new design. As we add some rounds to the base, note that all of the changes we just made to this model to transform it to the new design could have just as easily been applied to an imported model from another CAD system. Because synchronous technology directly modifies the solid model, there's no need to understand how the model was created or have access to the steps used to build the model initially. To create the large cutouts in the side face of the pyramid base, we'll simply offset some of the existing geometry of the base to use as sketch elements. The quick bar presents us with all the steps needed to create the feature. Now we'll just change the offset distance for the last offset. The intersecting sketch elements then become regions that can be used to either extrude or, in this case, cut away part of the base. To complete the cutouts, we'll add rounds to the corners to make it easier and cheaper to manufacture. To complete the design of the base, we'll simply create a pattern of the cutouts to the other 3 angled faces of the base. This is an associative pattern, meaning if later we change the cutout, the change will be reflected on all 4 faces. As we return to the assembly, it's easy to see that our square post no longer fits in the round base. This is not a problem with Synchronous Technology. Once again, we can modify the corner rounds to consume the flat faces and make a round post. Finally, let's use Synchronous Technology one more time to change multiple parts at the same time from the assembly. Now that's impressive. So the next time you want to create a new design, look around and see if you have an existing model that is similar, and using Solid Edge with Synchronous Technology, repurpose it for your new idea.
It doesn't matter if you're creating machined, cast, molded, sheet metal parts. Solid Edge with Synchronous Technology will allow you to create your models as fast as you think. I've just been briefed on a new spring clip that we need. So let's throw this design concept down. So we create this model, please pay attention to how much we work with our geometry on screen rather than clicking into commands the way it should be. By selecting more than one thickness face, we can create multiple flanges at one time. These flanges were created with a 90-degree bend. What if I didn't want them at 90 degrees? Look how easy it is to change the angle of both sides. Whoops, we really need this end to remain 90 degrees to each other. Solid Edge has tools to relate 3D faces like this horizontal-vertical relationship to move these flanges back to what I need. No need to undo, we have the freedom and flexibility for change. On this face we need a deformed feature. With Solid Edge we can create a simple sketch, go into the bead command, input all the values needed, and just like that I have a deformed feature from a single vertical sketch line. Now tell me that wasn't easy. On the top of the spring clip we need to add a rectangular cutout that will pass through all 3 of the flanges here on the right side. Nice quick way to create a rectangle, and a sketch relation will ensure that the cutout stays center. We can also place any key dimensions that we know at this point, 16 millimeters wide. By selecting the regions, we can simply pull the cutout through the part, but notice it's cutting through the end of the model, which we don't want. Instead, what we want is this same length of cut, but created before the part is bent into shape. No problem. Solid Edge can flatten a part on the fly before cutting. In this area we need 2 additional flanges. Again, we can easily change the angle of both of these flanges with the steering wheel. This is the main control for Synchronous Technology, hence its name. Around here on this face a partial flange is needed. If we grab the small arrow and start dragging, this will create a flange. In the toolbar there are options to move material inside, and yes, to also create a partial flange instead of a full flange. One additional partial flange is needed down on the other end of the part. But this time this flange goes upward. How about let's put the same size flange on the other side of the part? Yes, we can do that with the mirror command. When we created the very first sketch, we locked that sketch to the top reference plane. At this point, I've changed my mind and decided the top face needs to be at a 5-degree angle. In most other history-based CAD systems, this change would be a no-no because of fragile feature dependency. Not with Solid Edge. Pick the face, move the steering wheel, and rotate. Wow, that was easy. On second thought, we don't want this flange to be an exact copy of the first flange, so let's break the mirrored link. Yes, even though this is direct modeling, Synchronous Technology provides an organized tree with feature links where required, such as that mirror. Here we need to create a jog on this face. Just like everything else, it's simple to create with just a sketch line. While I'm at it, this flange could use a jog as well. Seeing as how we have all of these sharp corners, I think rounding the corners would make the part safer to work with. An 8mm face round will work. On this back flange, the width doesn't need to be this wide. If we use the long arrow, we can change the width of the flange and make the chain symmetrical from side to side. We need a hem here. Watch how easy this is going to be to create. Select the edge, enter a few values, and here we have a hem. So in a short amount of time, we were able to throw down this pretty complex design concept. And you'll be happy to know that even if you don't create sheet metal components like we had here, you still enjoy the same quick workflow, minimal sketching and mouse travel, but above all, ease of use. Push and pull to work directly with the design, and remember, no need to worry about what order should I do this in. You can modify at any time too. Solid Edge with Synchronous Technology Rapid Design. So you've seen how Solid Edge with Synchronous Technology allows us rapidly create initial designs. That's the beauty of direct modeling. But what about finalizing that design with precision parametric work? Synchronous Technology gives you the best of both worlds: fast direct modeling and precise control. Here we'll take our spring clip concept and ensure it fits and ready it for its detailed drawing. Let's take a look at how this will work inside Solid Edge. Here we can assemble this clip to our base part simply by selecting a few faces. Simple drag and drop, and Solid Edge knows what to do next. Definitely a time saver when working with hundreds of components. I have this in roughly where it needs to be. I can come back and get this exact when I start seeing the bigger picture. Here we need to assemble this USB block so we can tell just how much change we need to make to the clip. Notice all the nice visual feedback Solid Edge is giving me when selecting faces and axis of cylinders. first precise change we need to make is to close up this gap between the top of the USB block and the underside face of the clip. In most other CAD systems, you'd have to make this change in the 2D sketch level with sketch relations. In Solid Edge, this isn't the case. We can relate faces in 3D instead. Here, we'll add a coplanar relationship to close the gap. Easy, and know it's just how we do it. Looking at the back, I noticed the tabs on the top are not square to the top face of the part. No problem. A perpendicular relation will fix this small problem. Let's start detailing this model, and of course dimensions are key here. Solid Edge has two different ways to add dimensions. The first is like most other CAD systems, where you add sketch dimensions when creating the sketch. The second, however, is unlike other CAD systems and much more intuitive. Just add the dimensions directly to the model like you see here. A dimension can be locked to maintain that aspect of the design, or left floating so that we still have flexibility for further design changes. We'll lock this one down. The arrows allow us to control the direction of the change. What face or faces will move with that dimension. We'll add another dimension to our other tab and lock it down. Notice as we place this next dimension and change the value, the tab remains at the width we set it. We'll continue detailing our design with a few more dimensions. And it's not just linear dimensions. Let's detail an angle here. All of these dimensioning tools are fast, easy to use, and most importantly precise. What's more, anyone can understand them when it comes to a review. At this point, we need to finish working on the other end of the clip. Another 3D relation will do the trick to move and match the angle of the bracket. This tool that you see on the screen is called a steering wheel. With this, we can drag and drop these faces, accurately snapping them into place around the dimple. The final assembly relationship we need to lock the clip down is to line up the center of the slot to the center of the dimple. This spring clip needs to fit inside the groove of the USB block to hold it into place. Once again, a simple 3D relation between the faces allows them to line up precisely. To get the jog of the clip to line up, we could add the same type of relationship, or how about just a simple drag and snap using the steering wheel? One last subassembly to bring in is the inline fuse assembly. The tabs on the top of the clip will support the inline fuse, so we need to make sure it will fit tightly into place. Just like we saw earlier, putting parts together is easy in Solid Edge. Select the face, edge, or axis from one part and the same type selection on the other part, and they just go together. The side-to-side movement is not that important, so we can just drag it to a rough location. I know the wire diameter is less than 3 millimeters, so using the steering wheel we can create a 3 millimeter offset from the selected face before snapping it to the other tabbed face. This leaves us with a 3 millimeter gap, precisely how we want it. This area is too wide. A drag and snap to the end of the fuse will work. For dimensional control here, we can design to the inside or outside. It doesn't matter which one we change, Solid Edge will always take into consideration the material thickness. This outside dimension, I'll just take the default value. Now let's place a dimension to the inside. This dimension I know needs a value of 9 millimeters, and if you notice the outside dimension has updated to the thickness difference. Or I really want the outside dimension to be 10 millimeters, so we can change it and let the inside reflect the thickness value. The 10 millimeters is an important part of my design intent, so we will lock that dimension. Let's start creating a drawing ready for manufacture. First of all, let's create a custom view of the assembly so that all aspects of the part can be seen. And let's have that shaded. Now let's place a few views of just the clip. So remember the 3D dimensions we added at the part? Watch how fast I can bring those into this view. What we've seen here is how Solid Edge with Synchronous Technology gives you the best of both worlds. Fast, direct modeling and precise parametric control. Relating faces together, dimensioning with design intent control, and drag and snap editing. All in 3D. No sketch work in sight. Fast and easy, but most importantly, accurate.
In this chassis design, we depend on suppliers for some of the components. Now, many of these suppliers use other 3D CAD systems, so we need to be able to easily import their non-Solid Edge 3D data and make edits where needed. So let's go ahead and import our first component. And when I say import, in fact, all we need to do is click Open, like you would do in opening any other file. You can see here the many file types. Solid Edge can open files from other Siemens software such as NX, universal CAD formats such as Parasolid, STEP, IGES, and even other CAD systems such as Inventor, Pro Engineer, SolidWorks, etc. SolidWorks, this first component is from that system, so let's open that right up. Now we can easily apply a material as well as a finish. And in this case, our component is going to be painted orange. So importing was the easy part. What about the edits we need to make? Most other CAD systems rely on a history to be able to edit a model. But obviously, as this wasn't created in Solid Edge, we don't have that history, as you can see in the tree, or lack of it on the left. Not a problem, and no need to do any convoluted feature recognition. Synchronous Technology in Solid Edge allows us to make edits with a simple push and pull. This couldn't be any easier or intuitive. Click on a face and drag, and notice how the other faces that are in line with this are moving too, just as if it was a feature in a history tree. But what if you prefer editing existing dimensions instead? Sure, just click a face and Solid Edge will give you the dimension of that feature on the fly, ready to go to edit. Again, notice the intelligence of all the other holes changing as if it was in a pattern. I know, it looks like magic. If you want to add your own dimensions, you can do this in 3D. No need for sketch work. We need to set this thickness at 6 millimeters. Notice the control we have to keep this top face fixed. Now, one good reason for having a history of features in a tree is when we need to reorder rounds. You can see here that the previous designer created 2 rounds in the correct order, but these 2 incorrect with the wrong blend. Can we solve this in Solid Edge without a history? Absolutely. A simple right-click to reorder. Now, while we're here, we need to change the size of these rounds. By selecting one of these rounds, Solid Edge can automatically seek out other rounds in the same size. This way, we can save a lot of time by making one edit, not multiple. In some cases, though, you may need more than a dimension to edit, a good example being holes. Here we can tell Solid Edge to recognize these circular cutouts as holes so that we can change to a specific hole type. And in this case, we need counterbore holes here. And you'll notice it added the holes to the history tree. And as I walk over here and expand, you'll see that each one of the holes were created individually. What about removing geometry? Well, that's as intuitive as deleting files in Windows System. All we have to do here is simply fence select, and then with the quick right mouse button we can delete these features. So hopefully you can see how flexible Solid Edge is editing non-Solid Edge parts. By simply here selecting a feature, we can easily make modifications and Solid Edge will do the rest. Now here, of course, we're just showing off a little bit. Let's go ahead and save these changes that we have made. Now the next step would be to simply drag this directly into our assembly design, where we can position it with the rest of the assembly. Solid Edge offers tools that allow the user to easily get parts into the design. Now we do have other components to bring in, so let's just get this part close to its desired location. That looks good. Now our next component, a sheet metal bracket, was sent to us as a universal CAD file, Parasolid. We can import this in exactly the same way we did with the adapter. A simple file open. Now again, we have options to apply materials as well as different types of finishes. Now because it's a sheet metal file, of course we want it to look like a sheet metal file. Now, not only did we receive the 3D sheet metal file, but also its manufacturing drawing in DWG format. Wouldn't it be great if we could make use of this drawing to assist us with any edits and also provide the tolerance information all in 3D? Well, check this out. Once we open the DWG file inside Solid Edge Draft, we can then use a tool to get us to help us get this done. In this case, we're going to grab the information we need by fence selection and then apply that information to our 3D model. Now, you've already seen the steering wheel in action when we move geometry around. It can be used in the same way to snap the drawing views into position on this model. So Nice to see the manufacturing intent overlaid in 3D, but wouldn't it be great if we could control the model with these dimensions? Synchronous Technology and Solid Edge can do just that. A simple click to attach the dimensions, and now these dimensions are now live. Let's make some required changes. We're going to extend the flange to 35 millimeters, and then we can open up this flange to fit over the frame. We'll set it at 51 millimeters. Easy as that. So that we can send this to manufacturing, we need a flat pattern. But because this wasn't created in Solid Edge, how are we supposed to get this? Go back to the supplier? No, not a problem. We can tell Solid Edge to treat this as a true sheet metal part, flanges and all. This way, the correct bend allowance, etc. is known, so very quickly we have an accurate flat pattern. Now, back at the assembly level, let's go ahead and place this sheet metal file that we just created into position using the Assemble tool. Same tool as we used before. Now, the beauty of this tool is that it determines what type of geometry you select and then automatically filters the next assembly selection appropriately. This makes it very easy to get your components into position and fast. We can grab the cylinder. It's going to automatically align to the cylinder that we select. Here we want to get these two components placed into their correct position, so we'll first apply a mate and then finally an alignment, and that locks them into position. Now finally, let's get the drive motor attached to the assembly and then placed into its position. Notice the file name of this. Like the other components we've been working with, this isn't a Solid Edge file either. It's from Inventor. Using the same Assemble tool, we can quickly identify faces to mate and cylinders to align, making sure that our three new parts are locked into their proper position. And you can see that they are now. So once the motor is in its position, we can see right away we have a mounting problem. The two flanges don't match at all. No problem. With Solid Edge, a simple in-place edit allows us to grab geometry, sizing from one part and using it on another part. Now they match exactly, just as we would expect. We obviously need more room for fastening hardware. So let's go ahead and make some quick changes. Now first, let's get more room between the motor and its flange so we can add 20 millimeters to the throat. Just by fence selecting the geometry, keying in 20, it's going to move that geometry over for us. Now we need to change both parts together. Yes, that's right. A SolidWorks and Inventor part edited at the same time. At the assembly level, using the same simple push and pull we used before. So there you have it, Synchronous Technology in Solid Edge, allowing you to work with non-Solid Edge data as if it was Solid Edge data, importing just an open, editing just a push, pull, or delete, and you can even make use of 2D drawings along the way.
Design intent is the intelligence we as designers build into our CAD models so that they'll change predictably. The issue is, in a history-based CAD system, nobody knows what the intent is other than the original designer. This can prove to be problematic if the designer is no longer available or doesn't remember how the part was put together. Let's take a look at an example. Here we have a view and markup of an old part that needs to be modified. First, we'll make these changes as you would in most any other CAD system, using a history-based approach. Then, we'll go back and make the same changes using Synchronous Technology for comparison. For our first change, we need to add some extra material to the slide in order to create additional clearance between features. We have instruction to change our slide body to an overall height of 31 millimeters. As you can see, this feature sketch is fully defined and we can quickly make this change by simply clicking on the 29 millimeter dimension and then adding 2 millimeters to it. Solid Edge's dimensioning tools allow us to input formulas directly. Not necessary here, but we've all pulled out the calculator before. Due to inappropriate design intent, notice that our cut has been shifted. We'll need to go in and fix this. This can easily be accomplished by deleting out the incorrect sketch relationships and then adding new ones. Now let's go to our markups to see what the next revision is. Here we're having some problems with deformation within the cylinder and the bottom cutout due to material thickness. Therefore, we need to maintain 4 millimeters of stock between the cylinder slides and the cutout. Our first order of business is finding out how much material we currently have between the cylinder and the cutout. A quick measure gives us a value of 2.5 millimeters. We need to make this a total of 4, so we need to add 1.5 millimeters to the radius of the cut. Another simple change of our dimension value allows us to see that we need a radius of 14 millimeters. It's clear that the original design intent wasn't set up for this type of change, and we now have interference with our slide positioning holes. Undoing the change allows us to go back and alter the way the profile is drawn to correct the design intent. Unlocking this 1.7 millimeter dimension means that we can add a smart dimension between the bottom of the cut profile and the center point of the arc, ensuring that the material is added to the bottom of the cut rather than pushing the arc and the cylinder higher up into the part. Once our correct values are in place, we can see that we're getting our desired results. Now let's take a look at our final revision. We need to fix an issue we've been seeing from our new manufacturer while drilling these counterbore holes. We need to add a bit more clearance between the counterbores in order to not have any blow-through while drilling. For proper positioning in relation to the slide cylinders, we need to move both holes 1 millimeter in opposite directions of one another. In order to get a better idea of what we're working with, we're going to create a section view through the holes needing editing. This is a great tool for parts with complex internal geometry. Using the dynamic clipping plane option allows a section to be shown in any particular location on the part, as well as the geometry located within. Now that we can see where the blow-through is occurring, let's edit this front hole. Once again, by editing our profile, we can either key in exact values for dimensions or let Solid Edge do the calculation for us. Now that we've subtracted 1 millimeter to the front hole, we need to do the same with the top. Repeating the same steps, we notice that this hole is not defined the same way as the previous. This counterbore is modeled as a cut and is concentric to the smaller hole running through the slide cylinders. This sort of frustrating situation is often run into in history-based modeling. Design intent may not be what you naturally expect. It's all down to the original decision upon creation. Re-examining our part to make sure everything is how we need it, we notice that we now have an issue relating to the back cylinder. Again, the setup of the original design intent means that the model hasn't changed as expected. We anticipated the back hole to stay in line with the front hole edited earlier. As we look at the profile, we can see that the hole has simply been dimensioned to the bottom of the part to match the dimension on the front side. This independent type of design intent is tedious and time-consuming, especially on complex parts, and in certain situations, a simpler solution would be just to remodel the part from scratch. However, in this situation, a quick horizontal relationship fixes our issue. In summary, we've made the required revisions, but not without time-consuming interrogation and modification of the original design intent. What if Solid Edge could recognize the model's design intent automatically to give more sensible results during edits? Let's make those revisions again using Synchronous Technology. We can of course create our designs from the ground up using Synchronous Technology. However, if, like in this case, the design work has already been completed history-based, we can simply convert to synchronous. We just select the last feature, which will move it and everything above it in the history tree over to synchronous. The first thing you'll notice about working synchronously is that we don't have to edit profiles of any features. Instead, we can simply dimension directly to faces, and we have full control over which way the edit is intended. While we're making edits, you'll see the icons at the bottom of the screen light up. This is the design intent recognition. Solid Edge captures design intent based on the geometry without any additional work on our part. In this change, Solid Edge recognized that this part was created with the top and bottom faces in line with one another. If for some reason we wish to change the recognized design intent on the model, it's as easy as clicking on the relevant icon to relax those geometric relations. First revision done, and the design intent of maintaining a central position recognized. Our next edit is dealing with the clearance between the bottom cut and the slide cylinder. Using our dimension tool again, we can quickly pick up the two radii and choose which face we want to make the edits to. Locking them ensures that they're maintained after the fact. This time, notice that symmetrical design intent was looked after without any outside action on our part. Our final edit required us to use a section view in the history-based model. This was our means to see exactly what geometry and features we were working with. Now, what if we could take that a step further, automatically creating sketches at a particular section and allowing us to use those sketches to drive the model itself? I introduce you to synchronous live sections. Knowing that we need to add clearance between the counterbore holes, but also maintain the design intent further on down the part, we're not going to add just one, but a couple of live sections to the center lines to properly display and represent these features. Quickly turning off our design body, we now have an unobscured view for our required edits. We can simply drag this profile to see how the design intent is being taken care of, which of course is also modifying all of the solid geometry in the background, or we can use precision tools to make the edits. Again, we'll use the dimension tool to enter the precise value, choosing a symmetric input. Remember the multiple moves and multiple profile changes in the history-based approach? That's not the case here. To recap, what we saw here was synchronous technology and Solid Edge recognizing and maintaining design intent on the fly, giving us sensible and predictable changes, overall allowing for faster revisions.
Products are designed as a whole, not just individual components. This translates in CAD as the ability to easily edit parts at the assembly level. In this example, we have a solid edge assembly of a pulley system where we want to make changes to the width of the custom pulley because we are going to fit a wider belt. Of course, that means editing several other components also to suit. First of all, let's approach this as you would in most any other CAD system using history-based editing. After we in place activate into the part file, you will notice the list of the features on the left. Since I need to make the pulley wider, we can easily select the side of the pulley to make the initial edit. We see there is an overall dimension of 35, which I can change to 55. That makes this easy, or does it? Because there are dependent features farther down in 3, this change has caused these features to fail. Now we need to go back and try to understand what needs to be edited first so we do not have failing features. Let's just start by editing the hub height first and change the 10 mm to 20 mm. Once this is done, maybe we can go back and widen the wheel as we did before. This appears though it worked. But another issue is the thickness of the inner wheel is now too wide. Let's select the feature and push it back from 10 mm to 20 mm. Now those edits were easy, but you do have to figure out which features to change and in what order. So back at the assembly, obviously the wheel is now wider, which means it's interfering with other components, and we have some internal pulse to deal with too. To edit these, we could continue using a history-based approach, but this proved to be time-consuming because we'd have to modify each part individually. Of course, working with history-based part, we could set up links so that the other parts would update automatically, but that also takes time. We want something instant that doesn't have the overhead of interlinking. Let's turn to synchronous technology. First, notice we're staying at the assembly level. From here, we can pick a face and drag to edit. Solid Edge is intelligent enough to know that there is a symmetrical part and that we probably want to keep it as such. But what if you want to make several edits at the same time? Let's see how this works by selecting multiple faces from multiple parts. Here we can modify not just 1 or 2 or even 3, but let's edit 4, 5, and 6 different aspects from 4 individual parts. And still, Solid Edge is automatically seeing that this design is symmetrical. So actually it's doing double those edits for us. Also notice how everything else is changing sensibly. Tangent relations and wall thicknesses, for example, are all being maintained. That's what we mean by one-shot multi-part editing. Looking good and very quick. Another way to make one-shot multi-part edits is by aligning faces. Again, all at the assembly level. For example, we will rotate this view so we can see the backside of these brackets. We can then set these two faces to be in line very quickly. To take this a further step, we can ask Solid Edge to just as easily snap all those coplanar faces to this back face. Job done. So there you have it. No more in and out of each part with time-consuming history-based edits as you go. Synchronous technology in Solid Edge allows one-shot multi-part editing, accelerating your design. Here we have a view and markup of some unexpected design changes for our tank design. These all have come about from some late design changes made to the mounting frame, and so we need to make some adjustments to accommodate the new frame. The first change is to deepen the pocket for the hanger. First, we'll make these changes as you would in most any other CAD system using history-based approach. Then we'll go back and make the same changes using synchronous technology to compare. Now, some history-based modelers do have direct editing techniques, so let's try this type of tool for our first design change, moving the bottom of the pocket down. No good. Notice that this fails, assumingly due to some downstream features. This means then we have to go back in the history of the model and modify the actual cutout feature extent. As the model rolls back through the history tree, notice that we lose a lot of details on the left side of the part. This appears to be caused by the adjacent cutout features. This means we need to undo the change and modify the adjacent cutout before changing the one we actually need to modify. Notice that the depth of this cutout is being controlled by the hanger pocket depth. We need to break the associativity as the design intent of having these two pockets at the same depth have not changed. We can then go back and make the required change. Everything now appears to be okay. Back in the markup file, we can see that the next required change is that the face A needs to be in line with face B. Back in Solid Edge then, we modify the pocket cutout to match the edge to the lower pocket. Notice that as we roll the model back to the profile of the cutout, the lower pocket disappears as it is later in the history tree. This exposes another caveat of history-based modeling. It is now requiring more work of either creating additional geometry or reordering features such that they appear in the order we need them to be in, to be able to make the required change. After reordering the cutout, these gray arrows represent the warning of some kind of issue with rebuilding that feature. For now, we are going to ignore the warnings and continue with making the changes. However, ultimately, this needs to be checked. As we attempt to make the edges in line with each other, notice that there are some lock dimensions that must have seemed important at the time of the initial modeling that now need to be relaxed in order to accommodate the new design requirement. Once these are relaxed, we can successfully make the requirement alignment. Although the faces appear now to be in line with each other, we will now make a final check using the measurement tool. As we measure the angle between the faces, it is clear that there is a 2-degree difference in their angle. We can only assume that a feature down the history tree has been added, causing the difference in this angle. Once we find the feature, in this case the draft feature, we will need to edit the feature to include the faces from the upper cutout too. Imagine if we had not made this final check and just assumed the faces were aligned. What would it have cost our company to repair the tooling when it was discovered that the tank didn't fit? Note that adding this draft has impacted the rounds. Did we make the changes to the rounds? No, but in history-based modeling, as one feature is based on another, one change can in fact turn into multiple changes. This again requires to modify existing geometry to add these rounds back to the edges of the cutout. According to the markup, the next requirement is to reduce the overall height of the tank to 425 mm by adjusting the lower face. The reference dimension shows that the tank is currently 448 mm high. Our task is to determine which feature controlling the height of the tank the first feature it finds is clearly not the correct one. Instead, this cutout appears to control the entire bottom part of the tank. There is not a dimension from the top of the tank to the bottom profile, so we will need to add one, as this is not a new design intent as specified in the markup. The dimension comes in as a reference. This is because it appears that the profile is actually an offset of another feature in the part. We will need to delete the original design intent of the offset and then lock our new dimension to drive instead. We also need to add a relationship to ensure that the profile is still parallel to its previous location. As we display the overall reference dimension again, we can see that now we have the correct height. Once again, this change seemed to have caused us to lose more rounding on edges. We will edit the round features again to reselect the edges. Before moving to the final design change, are we sure everything rebuilt 100% correctly? Do you see any issues with the geometry so far? Something looks changed where we just reapplied those rounds. By switching back to the markup, we can see that the angle of the cutout is not intended to cut into the large pocket in the middle of the part. We will need to either undo the last change to try to see what is causing this to happen, or go back and edit the pocket to try to fix the problem we have now. In this case, we will try to fix the problem. In the profile, it's this lock dimension to the bottom face that's causing the entire cutout to move up. To fix this, we will relax a couple of dimensions and move the top profile down to where it was originally. Once again, if this undesired result of the moving and a related face is not caught at this point, it could have been a very costly mistake when tooling was made incorrectly. Finally, we need to increase the angle of the front face of the tank by 15 degrees to compensate for the loss of internal volume by the other changes that we have just made. We can see by using Quick Pick that the main shape of the tank is defined in the initial feature. We will edit the definition of the first protrusion and add the 15 degrees. Because this is a history-based model, every single feature will need to rebuild on the first feature that we just modified. As you can see, this has introduced some big problems. There is a huge gap going through the middle of the part. The mounting holes for the controls in the top have also shifted and some have disappeared. The red exclamation marks indicate features that have completely failed to recompute. We could have spent many hours attempting to fix this model, or maybe it would be quicker to start again. Keep in mind that this part was not intentionally modeled to fail, and it wasn't modeled wrong. It's just that when the design intent changes from what was originally deemed important, issues can arise with editing a history-based model. Let's take a look at how we could have made these same changes using synchronous technology. You can of course create your own designs from ground up using synchronous technology. However, if like in this case your design work have already been completed history-based, you can simply convert to synchronous technology. We will simply select the last feature, which will move it and everything above it in the history tree to synchronous. Note the message that the team file feature will not be associated to the outside of the part if moved to synchronous. While it's not necessary to do now, we will go ahead and delete this feature before moving to synchronous so that we can take a look at another powerful aspect of synchronous technology later on. As well as the geometry, sketch dimensions get migrated to synchronous. You'll find that some of these dimensions are actually irrelevant to the 3D geometry. These dimensions collect here so that they can be deleted in one easy step. Now let's make the required design changes on this fully synchronous model and see how it goes. In synchronous, we can apply product manufacturing dimensions directly to the 3D model to derive changes. Notice we can change our design intent on the fly by changing the depth of the pocket without modifying the depth of the adjacent pocket. Making the face of this upper pocket line up with the lower pocket is done with just a couple of mouse clicks. And because I have forced them to be in line with each other and there's no history, I don't need to worry that they may still be off due to another feature that's added later. The overall height dimension that was a reference PMI dimension in the ordered part is now a dimension that can use to drive the height of the model directly. Notice that the edit only affects the faces it is attached to, with no concerns of moving unrelated geometry like the pockets in the middle of the part. Finally, let's rotate the angle face out by 15 degrees using the steering wheel, and again note that only the relevant geometry gets changed. As promised, we'll keep the theme wall. The reason I left this until last is to show you this. As we create a feature, it gets added to the bottom of the tree as you'd expect, just like history-based modeling. However, you can reorder anything to anywhere in the tree, even this typically fragile theme wall feature. We could even make it the very first feature. This is because with synchronous modeling, we don't have an ordered list of sequential features. Features are simply a collection of faces that make up a set of geometry. So the best of both worlds, an organized tree but no delicate dependency. Of course, theme wall or not, design changes are made in the same way. Notice how that as we drag this face, our new design intent is correct with the other face maintaining alignment. This demonstration clearly shows the advantage of using synchronous technology to make faster revisions from unexpected design changes. Often occurring at the worst time late in the design cycle, there is no need for panic. No more annoying feature dependency, no more waiting for rebuilds. You can create a model once and edit forever, freely changing your design intent and editing only what you need to.